Oh, yes. Okay. Okay, so let's start first of all with the concept of structural catalyst. A catalytic reaction is a reaction where we're using something, a catalyst, which is helping in speeding up the reaction. Most of the catalysts are using a fixed bed configuration, but because of heat and mass transfer problems, most of the time it is even more interesting to apply the catalyst on structures and go, for example, for monoliths. That could be either ceramic or metallic. For example, the system we have to treat the exhaust gases in our cars, those are made of monoliths with a catalyst. But as an alternative of catalysts, we can also use foams, for example, where foams are, the concept is exactly the same, but the structure is completely different. You see, we have a kind of spongy structure. So the fluid dynamic is completely different compared to the monolith or the honeycomb. So what we are studying in POLITO is the use of basically open ceramic foams in comparison to monoliths, either ceramic and metallics, and we tested over there either exo and endothermic reactions. And they are very interesting because, let's say, they are compared to monoliths, they are offering a much larger specific surface area, so we can line more catalysts. We can make a thinner thickness of the catalyst. Foams are very porous. It means the overall void fraction is much higher compared to the monolith. They are very well resistant in terms of mechanical strength. They are also very light, so if we are thinking to a possible application on board vehicles, they do not, let's say, overcharge the weight of the vehicle, and this is very good for the traction of the cars. And thanks to the tortuous pathway, we can, let's say, improve the mixing of the reactants, and then we can improve the transport properties for the reaction of interest. We are also working on an interesting concept, which is the concept of the integrated reactor or microchannel reactors, where, let's say, using the concept idea of heat exchanger, we can couple endo and exothermic reactions together. So let's say the exothermic reaction can directly provide the heat to the endothermic reaction, so we don't have to provide extra heat for the reaction of interest. And here we have some example. For example, here we can study, for example, a water gas shift or a CO-prox reaction where we can remove the heat thanks to a refrigerating gas, for example, or a liquid stream. And in this way, we can control the exothermic reaction, or we can couple an endo and exothermic reaction, for example, a reforming reaction together with a combustion. Again, so the combustion reaction is providing the heat to the endothermic reaction. And in this way, so you see, we are using this kind of configuration. So microchannels, we are depositing the catalyst. This could be the same catalyst or different catalysts on the two sides. So in one side, we are carrying on the endothermic reaction, and the other side, we are carrying on the exothermic reaction. And in this way, thanks to this coupling, and there's only a very thin layer, which is constituted by the metallic plate, we can favor the heat exchange one side to the other. And this is also a very interesting application. So I will show you what we are doing in this case. And the two reactions that, let's say the two applications that we are studying in POLITO are one side, the methane steam reforming, which is an interesting reaction in the idea on the concept of the decarbonization, because with the methane steam reforming, we are producing a syngas, so CO and hydrogen, and thanks to further purification, we can also, let's say, reach a pure hydrogen stream. And the other concept reaction is the methane-linked combustion. It means the combustion of methane in very few concentration for environmental protection. For example, in the methane or natural gas fueled cars, where methane is the main fuel, methane is a very stable molecule, so we have some methane residues in the exhaust gases, and so we can put here a catalytic reactor to burn the molecules which are not burned into the combustion engine, and in this way we can completely transform the methane into water and carbon dioxide, and then reducing the greenhouse effect of methane, because we are not anymore emitting methane. But here we are in lean combustion because the concentration of methane here is very low, and then we are forced to go for a catalytic reaction. And what is interesting is that if here we have our substrate, it could be a monolith or could be open cell foams, so those are the foams, we are able to deposit a very thin layer of catalyst. I mean, let's say no more than 100 micron as a thickness, and in this way, so if this is the gas phase, we can carry on the catalytic reaction, and we can study all what is happening in our structured catalyst. So let's start with the example of the methane steam reforming. As I was mentioning you, this is an interesting reaction as an alternative to the production of hydrogen by electrolysis, for example, even because we have a lot of availability of natural gas. Now with the war, maybe not, but let's say this is a study that we started some years ago. So methane is very interesting because it contains a very few amount of carbon as atoms, and hydrogen is also very interesting, for example, as a fuel in the case of fuel cells, so there's very interesting applications, and hydrogen is not that dangerous as we are thinking, because it has been demonstrated that if we are considering a car fueled with gasoline or for example with hydrogen, the hydrogen car in the case of accident with a fire is less dangerous than a gasoline car, because with the gasoline the fire will hit the entire car, whether in the case of hydrogen, the flame is, because thanks to the lightness of hydrogen, the fire is escaping vertically, and the fire is not involving the car. So whether, let's say, the lightness of the hydrogen could be a problem for the storage, as you can see from this picture, it is not that much in terms of safety, even if, let's say, the flammability of hydrogen is very high. So anyway, the important is to be aware of the problems and to know how we can deal with those problems. So actually, hydrogen, most of the hydrogen, let's say 95% of the hydrogen, which is actually used mostly in industrial use, is produced by natural gas of steam reforming. And this is for sure the most efficient way to produce hydrogen. The problem is that we are producing also carbon dioxide, and so we need to sequestrate. So here, just to have a comparison, you can see the costs of hydrogen production by natural gas, depending whether you are starting from gases, whether you're producing gaseous hydrogen or liquid one. So in the liquid, of course, the prices are higher because of the liquefaction process. And if you are starting from other kinds of fuels, the prices are increasing, and the prices are even higher if we are talking about electrolysis, depending on the type of electricity we are using into the electrolytic process. But anyway, the point is that let's say natural gas can also be an interesting opportunity for local production and small production by using, let's say, fuel processors. Fuel processors are, let's say, small units that starting from a hydrocarbon, and we were studying, of course, methane. We can apply for several reactions of reforming, so oxy-steam reforming, steam reforming, or partial oxidation. So we are transforming the hydrocarbons into a syngas, where we have a lot of hydrogen, but also a relatively high concentration of carbon monoxide. And then this carbon monoxide can be reduced, let's say around 0.51%, applying for water gas shift reactions by adding water. And then we can even further reduce this low amount of carbon monoxide to few ppm if you are proceeding with another step of CO cleanup, where, let's say, thanks to the presence of oxygen, so by adding oxygen, we can shift the equilibrium, and then we can increase further the amount of hydrogen. And in this case, with this further step, for example, we can use the stream of hydrogen we're producing for feeding hydrogen PEM fuel cells, for example. And the point is that steam, as I was mentioning, steam reforming is a very interesting reaction because it is the most efficient we can apply into the reformer. So on this point of view, a couple of years ago, we had a cooperation with the University of Delaware for the concept of the integrated microreactor. So by coupling the reforming reaction, which is an endothermic reaction, with a combustion reaction in order to directly provide the heat of reaction to the system. So we were using this kind of metallic plates. So the concept is, as I was mentioning you before, the concept of heat exchanger, plate heat exchanger. So where on one metallic plate we have both sides channels. So one side can be used as a reformer, and the other side can be used as combustion. So, and we deposit here 5% platinum over alumina in a very thin layer. So here you can see this is a micro picture, so a SEM picture of the micro channels, let's say naked, so the metallic ones, and here with the catalyst. So you see the catalyst is very well placed in a uniform way, and for all the length of the channels. And this is the pilot plant where we that we were using. So we were feeding methane both sides. In one case with oxygen for the combustion side, and the other case with steam for the steam reforming reaction. So we were let's say coupling the two reactions and see how the overall system was going on. The tests we made were with only one channel combustion and let's say one side combustion and one side microplates. But in principle, we can repeat this sandwich many times by alternating one endothermic and exothermic in order to create the overall power and the overall amount of hydrogen stream needed by a possible application. Then we perform with a series of experiments by, let's say, proceeding with a concurrent feeding of the two sides, or countercurrent operations to see the effects of the two ways of looking. And here you can see at the combustion side and reforming side. So what you can see here is on the combustion side, here we were monitoring the conversion of methane, and you see for the time of stream, and you can see that we were able to completely burn the methane. So at the very beginning, the reactor was placed into a furnace to start up the reaction, but you see after a while we were able to stop the power provided by the furnace, and then here the reaction was proceeding spontaneously. But time to time we had to, let's say, provide some heat, so you can see the electrical power we were providing. And here we were monitoring the reforming side. So you see at the very beginning we started with the production of the syngas, but by proceeding the time, the reaction was slowing going down. So it means that's why we needed to, let's say, provide thermal input because the combustion was not enough to provide. And here with the concurrent operation, so again, the furnace was stopped here when we were able to reach a full combustion. And then the combustion side was able to self-sustain, but here also, you see this is the conversion of methane, and the drop was much more evident compared to here. And here you can see the amount of carbon monoxide and the hydrogen we were producing. So let's say we made those tests at different velocities, and in some cases, as I can show you here, in the countercurrent operation here, by monitoring the temperature, you see we had a series of thermal instabilities due to some flashback problems and extinction problems. So so those are all a series of flashbacks, and at a certain point, because of the we were forced to start again the power and then to provide external heat with the furnace. Whether with the concurrent operation, the operation was much more stable, and we were able to keep almost constant the temperature of the system. But in the concurrent operation, we formed much more NOx compared to the countercurrent situation. The point is that we tested experimentally only one side, and let's say even if the overall reactor was very well wrapped, and so we were able, let's say, to insulate and keep the heat of reaction. We also perform a series of simulations that if we are increasing the number of channels, we are able to overall provide more heat and keep the overall two reactions much more stable compared to one single, let's say, side combustion and one single side reforming. Anyway, let's say the concurrent, the concurrent way was much better compared to the countercurrent operation, because in the countercurrent I was mentioning you, we had a lot of instabilities and flashback and extinction, and so we need to provide extra heat from the oven. And that was one part. Another interesting part that we carried on together with CNR, which is the Italian Council of Research, and also the University of the País Vascos, the Basque countries in Spain. We worked on, and we made some comparisons, monoliths, ceramic monoliths versus metallic ones, for, let's say, the always steam reforming by using a different catalyst. So we were using ruthenium 1.5, because the previous experiments were done with palladium 5%, which is a quite high, but there the meaning was more to, let's say, test the concept of the reactor. Here we were more focused on the type of catalyst that we were using. So we use 1.5% ruthenium over a modified alumina with lantana to increase the thermal stability of the alumina, that we coat on ceramic or metallic monoliths. You see completely different configurations, because here we were using square or hexagonal channels, whether here with a fecraloid, to prepare the fecraloid, we use one flat and one corrugated plates, and we were rolled, kind of Swiss roll cigarettes. So that's why you see that here the configuration is very different. And we also wanted to investigate the effect of a different cell density. So 100 or almost double, so 170 for the alumina monoliths, and a little bit less than 500 or more than 1,000 CPSI for the metallic ones. And we made a series of tests. So first those are the ceramic ones, and those are those ones. So the upper part are the ceramic, and the lower are the metallic ones in fecraloid. So 100 or 461, and here the much more dense. And so we worked at 800 degrees as temperature and steam to carbon ratio of 3 with different amount of catalyst. So because we work with 4 different loadings, so 100, as you can see here, 100, 150, 200 and 250 milligrams overall of catalyst placed on the structures. It means that by keeping constant the overall amount of catalyst, we were varying the thickness and then the thickness of the catalyst over the walls of the monoliths. And as you can see here, we monitor here the conversion of methane, and you can see here that by increasing the weight Hori space velocity. And you can see here, if you are comparing the two alumina with a more dense number of cells, the conversion was kept at the maximum for much higher weight Hori space velocities. Whether for the metallic ones, not. And you can also notice, this is the scale grade, so black is the less amount of catalyst and green is much higher, that overloading the catalyst with 250 milligrams is making worse, whether the best loadings are around 100 or 150. So it means that it is not necessary to overcharge, because we are not able to use all the catalyst in the thickness, because then it means that we have some problems of mass transfer, internal mass transfer. And also here, we were able to evaluate here the residence time into the catalytic monoliths for those conversions. And let's say what we notice is that the methane conversion is limited by the internal mass transport. So that's why it is not necessary to overcharge or to go for very high amounts of catalyst. And this is good because it means that we can limit the expenses by, let's say, optimizing the catalyst loading. So you see the optimum loading is 100 milligrams for the ceramic and 170 for the other one. So it means that you see the thickness is around 60 because it was a little bit less than 60 and the other one was something like a little bit 80 microns. And also that we can increase the overall performance, and it means the throughput of the system by using a higher number of cells. So it means that working with a 170 CPSI is much better because it means that we have much more number of channels, and so we can better interface the gases with the catalytic layer. And then, let's say, those are the best situations that we were able to define with that one. And the same for the metallic. Another work we made, it was, let's say, the studying the reforming processes of biogas by using the ceramic foams. So very similar to what we made with the monoliths, we studied different types of cells with different voids. So you see the pore per inch were 20, 30, or 40. So here there's all the characteristics of the 3 types of cells that we use. And very similarly to the previous case, we deposited, in this case, we were using 1.5% over Syria, and we use the spray pyrolysis to deposit the catalyst over the foams. And so here you can see the foams, and here also the distribution of the metallic active site and the thickness of the catalyst here over. So we were able to, let's say, also with the previous ones were done by wash coating, but we are able also to obtain a very uniform distribution of the catalyst also by spray pyrolysis. And in terms of conversion, again here, so the 20 ppi and the 40 ppi compared at different space velocities. So you can see also in this case, we can confirm that if we work with a higher cell density, we are able to keep the maximum of the conversion of the natural gas with a weight Hori space velocity. There's no 30, but 30 ppi was very similar to 20. So here you can see only the comparison of the 20 with the 40. And on the 40, so here you can see the selectivities and the hydrogen production. So on the 40, that was the best one. We performed the reaction up to 200 hours. And you can see that the performance is very stable because there was no deactivation or let's say no decreasing of the activity by working at 70 as a normal liter per hour per gram of catalyst. And so let's say the performance we were able to keep. So you see more than 60% of hydrogen produced and something like 25% of CO, which is very good. And we also verified that we didn't have any problems of internal mass transfer limitation. But here, because we were able to deposit a very thin layer of catalyst. So also based on our previous studies, we here on the forms, we already went on amount in order to keep the thickness of the catalyst around 50 to 60 microns. And so this is the comparison between foams and monoliths for the endothermic reactions. And here instead, I want to show you the other application, which is the let's say the methane link combustion for environmental protection. So I was mentioning you, methane is a very powerful greenhouse gas, much more powerful compared to carbon dioxide. So even if carbon dioxide is a problem and we are trying to sequestrate it, it is much better to release into the atmosphere carbon dioxide instead of methane. And methane is a problem not only because of the cars filled with natural gas I was mentioning you before, but because in reality we have a lot of lean, so very few concentration of methane which are emitted, for example, in all the countries where coal is mining. Holland, for example, in Europe, but China, for example. We have emissions from, let's say, oil and gas and automotive, from the fossil fuel extraction. But also, for example, it's another interesting option is where we have intensive care of animals, of cows. They are emitting a lot, so it could be very interesting to collect all the air of the farms and to treat this air before releasing into the atmosphere to reduce the emissions of methane. So in reality, there's a lot of applications in which the methane link combustion can be applied. So here we can remove methane by combustion, but since the concentration are very low, usually below 1%, so we are below the explosion limits, and also the excess of oxygen is huge. We need to use the catalyst to promote the combustion of these very few concentration of methane. And also it is interesting to work at the lowest possible temperature in order to favor as much as possible the spread of this kind of process whenever it needed. And the point is that methane is a very stable molecule, and then let's say breaking the carbon-hydrogen bond requires a lot of energy, and in principle a very high temperature. In the past, within the group I'm leading, we were working a lot of methane combustion, and we tested many different catalysts, but we found a very interesting option by letting working in synergy palladium, in reality palladium oxide, in combination with a cobalt spinel oxide. let's say that we optimized at powder level, so by using small fixed bed reactors, this palladium oxide over cobalt spinel, where the cobalt spinel is a very interesting because it is able to promote, let's say, it has a very high lattice oxygen mobility, so it is able to provide oxygen to the palladium, which is very active towards methane combustion when it is in the form of palladium oxide. And so let's say we were using this ability of the spinel to keep palladium of the surface of the support as palladium oxide to promote methane combustion. And also palladium is very active. It is among the most active, much more active compared to platinum in promoting methane combustion. So let's say we worked a lot in, let's say, optimizing this palladium over cobalt spinel oxide. And so here there's a series of, this was, let's say, the main topic of research of two my former PhD students. And so we tested the optimized palladium oxide over cobalt spinel that we optimize in powder on different supports. So you can see here foams, ceramic foams, zirconia, carborundum, and alumina, and also monoliths made of alumina. And we also published all the results as results of the PhD work of those students. Here you can see the typical configuration of this palladium over cobalt, where you can recognize the typical octahedral structure of the cobalt spinel that we can also have replicated over the foams. So here you can see the characterization of the structured catalyst. So here you can see this is carborundum, this is zirconia. So you can see those are SCM pictures. So you can see very well the structure of the foams naked, so without the catalyst. But here with the catalyst, and you can recognize the very similar structures that you have here, this octahedral structure over the foams. So if I'm going and enlarge exactly on the surface, we can really see that we are able to replicate exactly and then to deposit the spinel, and by looking at the X mapping, also the palladium. And all the surface of the foam is very well uniformly covered by this palladium oxide over cobalt spinel on both types of structures. Then we tested the foams, and so the foams covered by the catalyst, also here 30 ppi or 45 ppi, towards the methane, the lean combustion. So by let's say feeding 1% of methane of 0.5% in excess of oxygen. And here you can see those are extinction curves for, and this is the methane conversion. You see that depending whether we are working with 30 or 45, and the results are different. And you see that either the red is the zirconia and foam, the blue is the carborundum foam. They are working quite well. Whether the foam made by alumina is the worst performing one. So we were quite, let's say, the amount of catalyst we deposited over the foams were exactly the same. So we were trying to understand why, what was exactly the role of the support, since the catalyst was the same, and the foam is completely covered by the catalyst. So there's no any intervention of the ceramic foam itself. And so we were thinking to, let's say, the different thermal properties of the foams, because SiC has thermal capacity very different from that one of the alumina and one of zirconia. So here you can see the test, and we made at different velocities, so 30 or 90 normal liter per hour per gram of catalyst. And again, and here we were focusing the attention only on the SiC and zirconia. And you can see by enlarging the figures that the behaviors are slightly different whether we are at low temperatures, so close to the 10% of the conversion, or let's say close to full conversion. And also you can see that when we are at a relatively low space velocity, the curves are very steep, so the conversion is very good, because in less than 350 degrees, we are able to completely burn methane, and there's no CO emissions. So the reaction was 100% towards water and carbon monoxide. So we were really attracted here because, as you can see here, the performance is very similar for all the monoliths except for the zirconia, which is and also here is not very well performing. Whether at a high temperature, yes. So we had the idea, considering the different thermal conductivity, which is 0.4 watt per meter per Kelvin for the carborundum, whether it is much lower for the zirconia, to try to understand what was the role of this thermal conductivity on the reaction itself. And because SiC, because it is very high, it is able also to transmit this heat, because it is very heat conductive, whether zirconia not. So we had the idea, and all of those experiments has been carried out in a reactor by using foams of 9 millimeters of diameter and 3 centimeters as length. So we thought, okay, what's going on if we are mixing the foams, and then instead of using zirconia or SiC, we are using a composition of both foams. And so we went for a mixed foams configurations where we used, always by putting SiC as first, considering the direction of the flow, and then zirconia, by using 1/3 of SiC and 2/3 of zirconia, half and half, or 2/3 and 1/3, so 2/3 of SiC and 1/3 of zirconia. The idea was to put at the very beginning, when the reaction, let's say when methane is coming, first one to encounter a very conductive foam with the catalyst, where, let's say, the reaction is starting. So somehow we need to ignite the reaction. So it would be very nice if the few molecules are reacting because of the catalyst, they are producing a few heat. This heat is somehow captured by the foam and released to the gas phase in order to enhance the starting of the reaction. And instead put in the zirconia, which is less conductive, and at the end, almost all the gas already reacted, so we don't need anymore the heat of reaction, but instead we would like to favor the exit, and then to put something which is less sensible to the heat produced, and then we put zirconia. And so we carried on a huge set of experiments with those configurations with the mixed forms. And those are the reactions. So this is, let's say, with the best combination, 3 different space velocities, so 30, 60, and 90. And so with this half and half, we were able to reach full methane conversion at a little bit more than 200 degrees Celsius. So much better compared to any single combination. And here you can see this is those are the T50, so 50% of the conversion of methane for the 3, so 1/3, 2/3, or half and half, or different. And you see that the best combination is when we are using exactly half SiC and half zirconia. And here there's a comparison, because if you are looking here, with this half and half, we were able to reach less than 200 as T50, whether we were at 300, and we are reaching a full conversion at 250 compared to 375. And also at the highest space velocity, we were able to gain. So the gain was lower compared to the 30 as a space velocity, but anyway, we had a gain. So by using the two different configurations with this, at the very beginning of the reaction, this very conductive foam, we were able to improve the performance. And based on this, we went for not proceeding anymore. Oh, yes. Okay. So we studied the mass transfer by using the concept of the overall resistance, so the external plus internal resistance and the bulk reaction resistance. So by applying this concept of the resistance, so the overall resistance provided by those three, we examined, as you can see here, let's say the presence of, as a function of the temperature, of kinetic regime, internal diffusion regime, and external diffusion regime as a function of the temperature, which is shifting and also enlarging. You see, I have a much larger kinetic regime if I'm increasing the weight space velocity, reducing the transition regimes, and also pushing everything at much higher temperature. But the point is that in this way, with this concept, we were able exactly to examine and then to let's say to see the overall resistance in the various cases. And we also evaluate exactly the kinetics of the catalyst that was let's say absolutely comparable to the kinetics we evaluated for the powder, for the PDO over spinel powder. We also evaluated the heat transfer by, let's say, applying for the Anderson criteria for the internal heat transfer and the Merz criterion for the external heat transfer. And you can see that in terms of and those are the three different configurations. So the best one is the orange one, so the half and half configuration. That practically we never have any internal heat transfer limitation. And here you can see the effect on the external heat transfer limitation. So let's say the structures are behaving very, very well in terms of heat transfer properties. And let's say, so on this concept study that we performed on the mixed configurations, and here you can see the half and half configuration, and those are the single zirconia or the single SiC, that by mixing the two supports, we were able to enhance very much the performance of our system. And this thanks to the different thermal conductivity of the two supports. The heat and mass transfer were very much enhanced compared to the single ones, and this is basically because we were able, I would say, to catalyze, or let's say to really use the few heat coming from burning the first molecules, which are being oxidized at low temperature, to, let's say, provide that heat to speed up the reaction of the following, and to really speed up a lot the reaction, and then perform the full conversion of the fumethane at very low temperature. And so this is a very interesting result that we obtained. And finally, just to conclude my talk, since, let's say, those foams are much more difficult in terms of geometry to describe compared to monoliths, especially if we want to perform some modeling issues, We, together with the EFP Energie Nouvelle in France, we performed a series of characterization by micro-CT in order to evaluate exactly all the geometrical parameters of the forms in terms of pore diameter, struct length diameter, and also node diameter, in order to try to recreate a 3D geometrical reconstruction of the forms that can be easily integrated in a model, and then to perform a series of modeling. So here you can see a series of micro-CT performed on alumina forms or carborundum forms or zirconia forms at different pore size, pore density, sorry. And here an enlargement where you can see the extension of the pore, and then all the geometrical dimensions that we were able to kept. And here all the, let's say, we made a huge number of measurements, so all the distribution of the measurements. From this kind of measurements, we were able first to determine a relationship between the node diameter and the struct diameter, and we compared those relationships with some other theoretical relationships available in the literature. And some of them are quite famous, as for example, the correlation of Inserra-Garrido or Lacroix, of also Camacho, that are quite used in the literature. But all of them are, let's say, used for some specific alumina or SiC, or for example, we didn't find any correlation for the zirconia forms. And also here you can see the ratio between the diameter of the node and the diameter of the structure for the forms. So our structures compared to the forms. And we also find out a correlation on how to correlate the specific surface area of the forms compared to the literature that we derived from these kind of micro-CT measurements. Those were very useful also to evaluate also in this case the thickness of the catalyst with the positive of the forms. And because of the very, let's say, tortuous pathway of the forms, we noticed that in reality the thickness of the catalyst is not that uniform as for the monolith, because there's some areas where you can see here we have a thicker layer compared to other where the thickness is much lower. So so what we can do, we can calculate. So by knowing the geometrical, the specific geometrical surface area, we can calculate an average thickness considering the amount of catalyst we are going to deposit. But in reality here, we realize that with the forms, it's not that easy to really provide a uniform layer. And then we use the geometry derived by the micro-CT in a series of multi-physics simulations, and we were using COMSOL to evaluate, let's say, our reactions and how we are going on, which is not that trivial, but let's say we are still working on that. So by concluding, we can say that these open cell forms are very interesting structures to carry on either endothermic and exothermic reactions. They are very interesting because of the very tortuous geometry, but also we can see that the influence of the nature of the structure, so the type of materials and the thermal conductivity can play a very important role on the overall reaction. So it is very important to study in detail what are the applications for a certain specific reaction. But anyhow, those kind of structures are providing much better transport properties compared to the monolith. And so they are very interesting alternative to monoliths in the optic of, in the point of view, or intensify a certain chemical process. with that one, I don't know what the time, if I'm on time or not. Anyway, I would like to thank my co-workers, Ercolino, Moncada Quintero, and Mazzei, that are former postdoc and PhD that are working on those topics in Polito, and all the cooperations with University of Delaware, the CNR in Messina, Universidad País Vascos, and Énergie Nouvelle, because all the work that I show you has been done in cooperation with several people around the world. And let's say, some pictures of Torino and Politecnico. We are located here in the northwest part of Italy, so you're very welcome to come. And I really hope that my visit here will be a catalyst for let's say, creating new exchange of students between Torino and Lisbon and Lisbon. And I thank you very much for your attention.